Good afternoon, everyone. Welcome to the Cloud Track 2 here in the Kodiak room. My name is J.R. Aquino. I lead Security Incident Response for the Cloud and AI division. And here joining us today is Ross from the Mystic team for doing threat intelligence. And we have a very special treat because this is one of the talks where Microsoft is going to be talking about Linux security topics. And so with that, I'd love to be able to give you guys a warm welcome for Ross and his talk on Linux.
Hello. I'm sure everyone here has seen this slide probably to death, but did you know that 40% of the VMs on Azure are Linux? Did you know that 80% of the world's largest banks run Linux? Did you know that LinkedIn and Skype run Linux? Now, Microsoft runs loads of Linux kind of VMs and has a massive Linux estate, and so do our customers. And the problem is that every minute we see thousands of attacks destined to these Linux machines. And for us, for our customers. So we need to protect ourselves. We need to protect our customers. And one of the ways we do that for our customers is with Azure Security Center. And so that's a little bit what we'll be talking about today and how we use deception to do that. So before I begin, some caveats. This talk is about Linux, but most of the kind of concepts I'm going to suggest are applicable to any OS. It's also worth saying that some of the slides may look like I'm attributing some attacks to kind of some individuals. No, there is no attribution in this talk. If you see pictures or things like that, don't take it that Microsoft is going to attribute this to kind of certain individuals. A lot of this is kind of raw threat intel, and some people could have been pwned themselves. Also, there's real URLs, real IP addresses here. Don't get excited and type them into your search engine of choice. So, Linux attacks, they're on a bit of a spectrum. Kind of on the right-hand side, there's kind of nation state, there's your advanced hacktivist groups, and on the left-hand side is your automated bots, and kind of in the middle is your script kiddies. This talk is about the left-hand side, not about the right. We do lots and lots of stuff on the right, but we're focused mostly in this talk along kind of the automated bots, which are a bit boring, but more interestingly is the kind of script kiddies. And they mount the kind of attacks against our customers that run up loads of Azure credit, landing customers with a massive bill, they steal data, and attack other customers. So really annoying things. And I don't think there's a name for this, so I call this EAPT, so extremely annoying persistent threats. So we see thousands and thousands of them per second. To represent this on a lovely graph, because I like graphs, this is just a small snapshot of all the commands that were entered into my sensor network over the course of a couple of days. And you can kind of see on the left, you've got the real massive botnets, the Mirai-esque ones. And they're typing in the same commands over and over again. So each bar represents a series of commands typed in. And pretty much everything on this screen is some kind of bot because they're just so prevalent. But if you look at the tiny red speck at the end there, those are real people. And by kind of mining data and having a look, I can tell you that kind of in the course of about a month, 77 real people had hands on the keyboard and were trying to attack people. And then these are 77 real people that make mistakes that we perhaps can use to protect customers. So what kind of attacks do we see? Well, there's generally kind of three. An attacker gets an exploit and uses that exploit and then immediately does some kind of action. Then there's brute forcing, plagues everything, every protocol can brute force. They get a credential, they install something, and that something is at the moment pretty much a coin miner. And then there's a third type, which is a little bit more interesting, which is brute force. They get a credential, and there is no attack. And then, days, maybe weeks can pass by, and then someone else on some other infrastructure comes in and kind of attacks that machine and installs some software. So for us to kind of use deception technology correctly, we need to understand this a bit more. Why does this third case differ from all the rest? And it comes down to kind of the dark web. And this is a shot from Dream Market, probably the most popular kind of site at the moment where you can buy kind of lots of different things. And if you type SSH up there in the corner and hit enter, you can buy kind of SSH creds to machines on the internet. Just there. You can also buy tools to kind of find your own creds as well. Lots of other things for sale on here, but I'm concentrating on those kind of SSH creds because that's really prevalent to our customers. And doing a bit of a translation there, it's about $5 for a fast machine, so you can use someone else's infrastructure to get your Netflix or whatever. You can also buy things like billing databases. So this is a VoIP provider's billing database, and that's about $38. So these are really happening today. These are kind of real screenshots from about a month ago. So the ultimate question here is, now we know a bit more about the attacks, how can we use deception to help prevent it? And the first thing is kind of, what is deception? Well, it's an emerging area of InfoSec that's been about emerging for the last 20 years. Most people have heard about it from honeypots, but there's loads of different techniques in there as well. And Microsoft have got a bit of a history on this. So 2 years ago, Daniel Edwards was presenting about the results he found from putting up honeypots. And then last year, Tomatella put some things out, kind of honey tokens or canary tokens, you might know them as, which kind of shows how Microsoft use this kind of technology. And I've taken this and kind of taken it to a little bit of another level. So really, really briefly, what are we talking about here? It's honeypots. But not just any kind of honeypot. But first, real briefly, a bit of a refresher, the three basic type of honeypots. You've got low interaction, which is effectively just Wireshark. You put Wireshark in a box, you get the results, you make pretty graphs, you might be able to kind of determine trends, that kind of stuff. You have medium, which is, medium interaction is a bit rubbish. It's, you write a bit of code to do just enough to do perhaps the authentication, collect a little bit more information. And then where most of the industry is at the moment is with high interaction honeypots. And this is, a Linux VM. It's, on the network, it gets attacked. As soon as it gets attacked and they brute force those creds, they tear it down and put a new one. And, take that information, call it threat intelligence and find someone to buy it. But the big problem is that, pretty much all honeypots are broken. Like, fundamentally, a honeypot kind of tells you about the attack and not the attacker. And they're really easy to spot. So if you port scan a honeypot, then chances are it's got about 200 ports open. They're trying to get as much data as possible. You can go on Showdown now. You can type in the IP address of a machine and see if it's a honeypot or not. And attackers do things like they land on a box. They'll send some packets out, and they'll check to see if kind of like what's my IP from a machine is the same as the IP they've come in on. And loads of the big providers are caught out by this stuff. So the information you currently get from these high interaction honeypots isn't all that good anyway. So we know we're being attacked. So can we use this deception technology rather than kind of alert us to an attack that we know we're going to get, but actually get it to tell us more information about the attacker rather than an attack? I put it to you that attacks change all the time, but attackers probably don't. And at Mystic, we try and take a lot of these processes and apply them to kind of APT groups. Can we take some of the things we've learned by tracking kind of state-sponsored groups and their ilk and apply it to kind of the script kiddie range? To put this another way, when you're a defender defending a network and you receive and kind of use this honeypot threat intel, what you're given is pretty much kind of this. If you can imagine like an attack is like almost like a playbook or a flow diagram of what an attacker would do. Log in, write this command, do a decision based on it, do another command. If that worked, do this command. And at that point, when you're looking at kind of traditional high interaction honeypot data, you only get success states. And kind of this is really annoying because understanding kind of the other kind of states an attacker could get into, understanding what's hidden underneath that fog of war, is the key to understanding what kind of attackers are doing in the first place. And if we don't understand what attackers are doing in the first place, then it's kind of game over for us. Kind of what I want to do is kind of force attackers to make difficult choices. And those difficult choices might get them to reveal different infrastructure. And if we've got different infrastructure, then potentially we can make their kind of what they're doing more expensive, or reveal kind of infrastructure, predict infrastructure they might use in the future. So, how do we lift this fog of war? Well, I'm going to present to you kind of something a bit different, and that is a hybrid honeypot. And what the hybrid honeypot is trying to do is kind of lift this fog of war and show all the different states that you can get an attacker into. We can get our only success state from our traditional honeypot data, but imagine if every command that an attacker entered failed. Well, that would give us kind of these failure states. And what we want is something in between both of those. So rather than doing what everyone else is doing, which is creating a nice machine for the attacker that always works, I want to trap them in a maze. I want to monitor their progress, kind of track them, almost like a rat. And that's why I liken this to a maze. And if you kind of know or understand graph theory, you could think maybe this flow diagram is kind of a connected weighted graph. So what is this hybrid approach? Well, it's trying to combine the best of each kind of honeypot kind of interaction level, low, medium, and high, along with specific technology to deceive attackers. And by deceive them, this is, at the human level, trying to get them to do some other behavior that we want them to do. We're trying to enumerate an attacker's behavior, and we're doing this by fault injection. So what does that mean? So what happens if you type wget, your URL, and it doesn't work? Well, chances are you might use another URL if you're presented with the right information. What happens if you landed in a box and you tried to compile your exploit, and then you ran out and it crashed? What happens if you landed on an old OS that would be really difficult to emulate? Or a really new OS? This is what the hybrid approach is trying to do. And then we're going to use this in addition to current high interaction honeypots to catch all the different raft of behavior an attacker would use, and do this to kind of predict new infrastructure potentially. You'd think that coming up with the faults that would cause an attacker to make different choices in this flow diagram would be really, really difficult. One of the things I'm here saying today is it's not. We can get inspiration from loads of other domains and pick up the rules that other people are using. These are domains like sales. So salesmen do this day in, day out. They go on a training course and they'll tell you need to know your audience, create problems and solve them, agitate and solve. When you're injecting a fault, include a reason why. And they have the kind of the concept of scarcity and reminding people that the choices they're making are theirs to kind of build confidence. There's other places to look, like magicians. They say, never reveal the secret to the trick, practice to perfection, and don't repeat the trick in front of the same audience. Frank Abagnale said that smarter people are more gullible. This is kind of good for us. And the former head of international hostage negotiation at the FBI, Chris Voss, said, the idea is to really listen to what the other side, aka the attacker, is saying and feed it back to them. And Social Engineering, The Art of the Human Hacker, the book, says, listening is a major part of being a social engineer. So that's what we need to do and implement that in our honeypot. And if you're interested in what people are doing in real life, just go on YouTube and have a look at people who are scamming the Microsoft technical support scammers. And they put great videos up on there, and I've been very inspired by them. But also, casinos, they are experts in the art of influence. They've got tricks to keep you in the casino, tricks to distort your body clock, tricks to make you think you're richer than you are. And how do they do this? Well, they placed services strategically. They've got near wins that keep you spinning for the jackpot. Everyone sees the big prize in the casino, but also they try and give you a sense of control. And then finally, game theory. This is an emerging area. And I talked about mapping behavior onto kind of this interconnected graph. And game theory is all about kind of taking this graph and treating kind of these things, information warfare as game, and can we model good and evil? And the limited work that is out there at the moment says, you can map kind of this behavior onto game theory. And what they found is, their optimal strategy wasn't kind of purely random. It was to kind of make machines that don't look like the most obvious targets, but not the least. So something in the middle. So crucially, can we take all of this and implement it in the language of our choice? So I've come up with a few rules, which are kind of, don't create the most or least vulnerable asset. Create a variety. Think carefully and place these strategically. Listen carefully, and this is the crucial one. That means high instrumentation of whatever you're doing. Don't reveal the secret to the trick, so obviously demonstrate these things to different groups. And let attackers see these big wins, but keep providing them small ones so they keep playing the game, as I call it. Knowing the audience, which is threat modeling, including reasons why when we inject faults, and where we can kind of create problems and solve them, this kind of agitate and solve approach. So these are the techniques that we'll be implementing: lies, persuasion, mimicry, distraction, traps and decoys, lures and breadcrumbs. This is everything society tells you not to do. And I want to take these techniques and implement them in C# and use them to get attackers to make different choices, move them around my maze, change the weights in my graph, and so I can get more interesting threat intelligence. First off, we need to start with our threat model, and this is pretty simple. I'm not after bots. I can create a simulation and the bots won't care. They'll just type all of their commands in, and that's all they know. So I'm not really after those. No, I'll get them for free. I'm not after state. They'll never find the simulations I'm putting on the internet, and they're not really after them either. They put too much time and effort behind the prep work, and if they even got into them, they'd spot it pretty quickly. I'm after this middle ground. Real people, these 77 real people who are kind of creating these attacks, these script kiddies. And what do I want to do? Well, I want to take time and resources away from the attacker and divert them to my honeypot infrastructure. That way, they're not attacking real systems. Now, I want to make it so expensive for them to attack people that they stop doing it. And I hope that the accidental result of this is, the creds on the dark web cost more or attacks go down. This is what I'm after. But before you go out and kind of build all these things, it's worth saying that I talk a lot to kind of our lawyers, and when we're putting these things on the internet, we need to be really mindful that we're not creating victims. We're doing this to protect customers. We don't want to be involved in an attack, and that's quite crucial. And if we can, we want to protect everyone, not just our paying customers. Everyone can benefit from this. But crucially, we don't want to be involved or be used to carry out an attack. So, what did I do? So, I implemented an SSH server in C#, and then on top of that, built a kind of bash/Linux simulation, 100% C#. You can putty into this. You can SFTP files, WinSCP files. You can start Docker images. You can connect to the database. I also log every TCP SYM packet, so I can get the best from those low interaction stuff. And you would think that implementing a decent Linux simulation that would fool attackers would be really, really hard. Maybe it was a bit. But you can use the techniques I've talked about, lies and mimicry and distraction in your implementation. First of all, only implement commands attackers are going to use. And then, the commands they're going to use don't have to even work. Most commands that are successful on Linux don't print a response. So, we get a lot of commands for free by not doing even anything. The most complicated ones we can show canned responses, and the even more complicated ones we can write a bit of code to do it. The testing for this is quite easy. You can point it at our simulation and a Linux machine and make sure you get the same data. Crucially, there's no VM at play here. Nothing is ever executed. So how does it work? Well, everyone gets to log in. You get 3 attempts, and you will always log in. Whatever username or password combination you try, we give you 3 attempts. I'm not interested in collecting username and password combos. We've got other things to do that. I want to let you in, but I need to provide a little bit of a barrier. I randomize the OS and the kernel, so I could be Ubuntu for one person, I could be Red Hat for the next. And I don't know if you've heard of kind of cost of goods sold, or COGS, but this has got really good COGS, because in a high interaction honeypot, you have to spin up a VM, and there's lots of maintenance surrounding that, whereas I can spin up thousands and thousands and thousands of machines kind of on demand, these kind of fictitious machines. And then, commands are typed in, and you get results. Now they're either canned or programmed. So we've hosted these VMs which have this software on loads of different data centers in Azure, because we need to protect ourselves. That's a bit of a no-brainer. Also, we host on other providers as well, because we know that attacks that affect kind of other people will probably affect us tomorrow. And this is all for Azure Security Center. And that product, it doesn't matter what infrastructure you've got. You might have some boxes that are on-prem, some boxes that are on kind of other cloud providers, and we want to protect everybody. So we're kind of agnostic to providers. Remember what I said about game theory and casinos? We want to strategically place these assets. So that's what we've done in lots of different data centers all over the world. The problem is I log so much data that I don't want to be responsible for managing that in any way, shape, or form. So I use log analytics. I take all this data, push it into log analytics, which is great, and then I can query things really, really fast off the back of that. The data we get, we process this with a few internal tools, but also if we see URLs or files, we'll chuck that into VirusTotal, because there's no point just us benefiting. Everyone can benefit from that. If we see attacks that we can take action on, because they're customer VMs hosted on our infrastructure on Azure, then we can send reports to MSRC and get things taken down there. So going a little bit into kind of the data side, if you haven't seen Custo, there's a Custo query there, and Custo is absolutely great. You can query things really, really fast. I can query kind of many, many gigabytes of data, in real time pretty much, and that's just a query that will give you the top 5 username and password combinations. But you can take queries like this and you make wonderful dashboards. So this is my honeypot dashboard that gives me kind of trends over time. So I talked about my SSH implementation, and I talked about listening carefully. But what does this actually mean? So if we apply this to an attacker, it means we've got to re-implement things from the ground up to really get the maximum value out of what we're doing. And you don't get this with high interaction honeypots at all. You're running somebody else's code that probably doesn't have the instrumentation. So a little bit about SSH. It is horrendously complex. I won't recommend anyone else implement it. It's remote access one moment, it's a proxy the next. It has file transfer capabilities kind of baked in. It starts a little bit like SSL or TLS, where kind of both sides exchange the cipher suites that they want to kind of use, and they agree on that. And then messages are produced by the client, handled by the server, so pretty simple after that. And then it's got lots and lots and lots of kind of client-specific extensions that crept in over time, mostly kind of putty ones. So what do we get? What's the point of doing all this re-implementation? Well, we get loads of information that we wouldn't otherwise get that may or may not be interesting. So kind of cipher suites kind of that are in use on the attacker's real machine, kind of the agent string of their SSH client, which can be really interesting. Kind of terminal modes, kind of real specific Linux things that the terminal they're using actually supports. And things like their terminal size. And there's no smoking guns on this information, but it's interesting to know. We can even, in some cases, get the user's locale, which is can be quite useful for maybe kind of geolocating kind of an attacker. But I can get other things from that. What about your uptime? Because I record the first packet that comes from the attacker, this packet is really special because it's come from the attacker's machine. And the TCP standard says certain values need to be present and they need to be generated on the attacker's machine. So magic fields like the time to live, the window size, and the TCP timestamp kind of give us interesting information. We can work out uptime. We can work out kind of the attacker's real OS, even if they change their agent string. And the TTL gives us a kind of a good approximation about how deep they are into a network, because it's kind of decremented every kind of hop they do. Yeah, so this is great. And what is the point of all of this? Well, now we have our SSH implementation. We can use these tiny sources of entropy in the protocol, the ciphers that we found, terminal modes, all those kind of things, and collect it together. And we can use it to build a fingerprint of the infrastructure that an attacker is using. This is great because if we see an attacker over there, the maximum we get out of it was an IP address before. But now we can use this fingerprint and say we know it's the same software being used over here as over here. So that's good. And I've said we can work out the real OS and how deep they are and all these kind of things. And we can do things like compare them to the agent string they're sending. So if I see an attack that comes from an agent string that says it's putty and the underlying OS is Linux, I know some weird things are going on. And that's a telltale sign that something bad's happening. But what if I told you I could get someone's public keys? If you have an authorized key in your keyring on kind of Windows or authorized key file on Linux, every time you connect to a remote host, the remote host can take those keys and check to see if you can log in with them. And that's exactly what I do in my implementation. Attacker provides their keyring, and I say, nope, that's not a key that can log in, nor that one, nor that one. And what kind of people like Ben Cox have done is built kind of databases of these public keys. And then there's a link there to a service where you can log in, it'll tell you your ID. And the great thing here is that if we had a database of everyone's public keys, we could then start finding out who is really doing these attacks. Well, maybe, attribution aside. And there is one such database. GitHub allows you to pretty much download everyone's public key as a matter of course in order to make the service work. And so that's exactly what I did. I've got a fairly large database of everyone's public keys. And every time someone logs into my honeypot, I enumerate all the keys on their system and then compare it to what I've got. And I'll show you some results of that later. But back into kind of deception technologies. We need to start, when an attacker logs into a honeypot, they're already decided that this machine could be a honeypot. So we need to reduce their fears over the environment. In a con, they call this the put-on. And in deception technology, we need to kind of do the same thing. We need to kind of tell the attacker, kind of not in words, but in actions, that this is a real machine. Attackers already do this. Like some phishing sites have GDPR warnings on the top to make people think this is legit. So how can we do this in our fake Linux simulated honeypot environment? Well, I found the best way is a legal disclaimer. So, that's a good thing. You see that an attacker would think, oh, you wouldn't put this on your honeypot by default, would you? So that's one way of doing it. How can we make this even better? Well, the answer is making it extremely long. Because the longer you put it on it, the more likely it is to come from an organization that has mandated policy for this. So that's what we want to look like. What other things we can do? Well, inject faults will cause us to get more URLs. So the idea is that if you try and wget something with one URL and that fails, that an attacker will probably use other infrastructure. And we want as many URLs as we can, but we can't get too greedy. So we use the rule of 3. You get 2 kind of faults, and then the third one appears to work. Another thing we do is try and enrich the data that we're getting from these attackers. And a good example of this is kind of zip files. Loads and loads of malware, Linux malware, will be delivered in a zip file because the attacker finds it easy. The problem with that is there's not a lot of metadata that I can get out of that zip file to be able to do further processing on it. What we want is tar files. Tar files have loads of metadata. And here's an example of 2 kind of real attacks and the tar files that were delivered. And you can see we get a little bit more information. And this is, potentially the username of the person who created that archive. So how can we make someone use tar over zip? Well, this is incredibly simple. We just say that, zip doesn't work. And instead, you have to use tar. And there can be loads of different messages we put into that. So, that we're not using the same trick every time. Another thing we do is we try and track stolen data. So we seed our environment with files to make it more valid. And when attackers break in, chances are they nose around, because why wouldn't you? And we want to track this information. We want to know where it goes. And crucially, these honey or canary tokens, before they've been used to kind of warn you of an attack, but we're on a different standpoint. We know we're being attacked. So can we use this for tracking instead? And the answer is yes. Here's an example of some of the files we put up, and someone will download link.txt, and they'll type the link into their browser, and hopefully it will be on different infrastructure, and then I'll get a warning in my inbox saying this thing's happened, and then we can use that to get more information on how an attack is being run. But it's just not enough to put files up there and expect people to click on them. We need to do this we have to practice our lures. So if you do that, if you create a directory with important files and put invoice.txt in it, first of all, no one's going to download it, and second of all, they'll blacklist your IP address because it just looks so weird. We want to do things like this. We want to get an attacker to find that file themselves, because if they find it themselves, they will believe that they found something that perhaps no one else would have seen. And we use every trick in the book to try and make this the most attractive file to download. So I've ringed a few things there. Most colourful icon, largest file name, the file sizes are tricking the eye into making it a bit arrow-like. The timestamp really stands out, so does the group and the directory it's in as well. And we do all of these things to draw the eye to that being an interesting file. And one other technique we use is scarcity. And salesmen use this really, really well. And we've only got 1 car left at this price, so you better make this choice now. How can we map this onto something that we can take and put into our honeypot? Well, there are a few ways of doing this, but the best one I've found is this. Your machine is going down for reboot. You've got to do something quickly, otherwise you're going to lose access to this. This, combined with other techniques to make it a high-value proposition for them, really works. Crucially, we're doing things like we've got scarcity, but we're also giving a reason why. Scheduled reboot. This machine will come up again, and you might not have access to it. So I've implemented this. I've been running this, I think, since about May. And the good news is that Shodan doesn't think I'm a honeypot. So that's really good. So it's all about the results. It's not enough nowadays to collect all this threat intelligence and have a massive database. You've got to do things with it. And I want to show you here 2 real attacks that I've slammed together into a bit of slideware. This is what you get from a real high interaction honeypot. This is an attack. This is what you would see. This is what you would write your detection logic against. And it's not very much. There's a lure in there, and there's a disclaimer. But I want more stuff. So this is what you will see if you put deception technology onto it. Things don't work. Some commands work, some commands don't. We can't use unzip because that's not there. We're changing targets, attackers' behavior. We're injecting faults, and we're introducing scarcity. So we're building confidence. We have our lure. You're on the billing server, and that's the big win. We're including reasons why faults occur. We can't find libzip, but we found libgz and libbz, so maybe you should use those as well. We're using the rule of 3 and with small wins to keep them playing for this big prize. We're enriching our data where we possibly can, and we're using distraction and scarcity to make them make mistakes. We've already done our really good listening. So in addition to all of this here, we get their real OS and we get public keys. I love metrics. I metricize everything. Are we doing a good job with this? Well, let's have a look at unique URLs entered just by real people. First of all, there's got a trend line that goes up. That's good. And statistically, there's a constant error in this graph because some attackers always use kind of some randomness in their URL. But things are getting better. We are collecting more URLs from people who are logging in, from real attackers. And we put these in our internal threat database, and we send them to VirusTotal so kind of everyone can benefit. But let's have a look at time spent by attackers in our environment. And that's going up as well. So this is over about a month and a half as we're deploying different deception technology into our sensor network. It's a 12-hour graph. And what you can see is that there is a gradual trend up. And it's worth noting that a lot of these kind of attacks at this end of the spectrum, these are smash and install operations. You get your creds, you get in there, you put your malware down, you get out. So the fact that they're spending more and more time, that's really great for us. We've gone up from about 1 minute to a little bit over 2. And in some cases, there's some really high outliers in there, which is good. What are the ways that I've proved that I'm doing a good job with this? If we compare the IP addresses that we've got to get from this technology and then query our own internal threat databases, and then what do we get? Well, I sampled 100 IPs that I've seen through this infrastructure and compared them to our other databases. And about 20 to 30% were already known by other sources. So we're definitely adding value by doing this. What about some real attacks? Well, we found there was an attack, came in from DigitalOcean, attacker tried to install a coin miner. Not that interesting, to be honest. Now, I get to see the attack, the commands they're typed in, the Monero wallet they're mining against, but ordinarily, from our kind of data sources, that would be all we see. But this attacker also downloaded link.txt. And they took link.txt and they used different infrastructure to kind of visit that URL, so a clean IP address. And that IP address linked them back to Romania. So that's really good. We've got additional information that we would not otherwise have got. There's some kind of other cases of attackers, testing their infrastructure. And I didn't even think when I did this kind of query that I'd get anything back. But I got 2 different attackers testing their infrastructure. And then you can go onto your search engine of choice and Google those and find the actual script that was used in that attack. And then you can find the author, and you can track that author back to, GitHub. And then you can track that back to maybe WordPress dumps they've done in the past, databases they've compromised. And maybe you track them back to Instagram. Maybe you track them back to their Steam profile. So at that point, we've linked, someone testing out their script. Maybe attribution is hard. Attribution is really hard, people. But we've maybe found the author of that attack. Now, I really love public keys, and I've been collecting public keys for about 2 months. And I'll say attribution is really, really hard. And when we're using these keys and kind of comparing them to our database, the person themselves might not be an attacker. They could have had their infrastructure compromised. This all could be fake, put up by attackers for our benefit. But let's see where kind of it goes anyway. So the first hit I got me back to someone's GitHub page. And I got their real name and their username, which I've kind of blanked out there, which is real information that I would otherwise not been able to get. And then I got someone else, and I got their picture and their full name and lots of other things. And it's really common, I'm sure you do it as well as I, reuse usernames between different services. And I'm quite bad because I will take usernames that I find and then type them into search engines and find people's Instagram pages. And then I'll go through their Instagram pages and I'll find the photos and geolocate their photos. And in this case, I think I found the actual keyboard that was used in the attack. Maybe attribution is hard. Now, is this a bad person? I don't know. And I'm not here to say this person is bad or good. But infrastructure related to kind of these accounts was used in this attack. And what else do I see? Lots and lots of proxying. I see Android kind of user agent headers, kind of Android traffic. I see kind of your eBay searches, that's yours, I use attackers, and I see kind of Amazon things as well. And why do I get all of this? Well, it comes back to the dark web and that people are using some of these services to kind of proxy traffic. They're literally breaking in and deciding to proxy all their traffic through there, which, quite frankly, I think is madness. But hey, what else do I get? Well, I'd say probably by and large is C2 traffic. And this is a quick example of an attacker communicating to their WordPress backdoor. Because you certainly don't want to talk to your exploit server by your home IP address. You want to use someone else's infrastructure. And I see, this is by far and large what I see the most of. But it's not all good. Bad things happen. And, I talked a lot about creating lures and making them really attractive. Well, if you repeat the same trick to the same person twice, they might find out. And this is exactly what this person did. And they left me a message, and that wasn't good. And this, for me, is a bit of a failed state. There was a glitch in the matrix. We did something wrong. So at this point, I'll go and find kind of the related sessions. I'll understand what happened, and I'll add commands, change output, etc., to put this attacker back on the kind of right path. But sometimes you get into weird states. This attacker was looking to see if this was a honeypot machine. And they ran this command, and they decided there was something that they didn't like about the output of this. The file I put there was wrong or something. And what did they proceed to do? They tried to nuke the box. They're catting dev random into the RAID array. They're deleting the default route to the internet and then rebooting the machine. So you may think this is also a failed state, but it's not, because the attacker thought it was real. Remember, this is all 100% C#. This is all fiction. It's 100% simulation. So the fact that attackers think they're going to have these effects kind of shows that I'm going down the right lines, hopefully. And it also makes me think that a person got quite angry, which it's wasting their time, so they're not attacking our customers, so that's good. In these kind of cases, what I'll do is I'll take all the infrastructure down, recycle the IP addresses so they don't put us on a blacklist or something. Another good example is when someone spent 10 minutes trying to fix the DNS resolver. And looking through the commands, it was like, you can feel the sense of terror and dread. And this is great because I know this person's only got one set of infrastructure and he's kind of desperate for it to work. In the end, they just got disconnected because you've only got a few. We only give attackers 10 minutes or so to do this. So we get all this data, and what do we do with it? Well, we use it to inform and develop detections for Azure Security Center. And this is Azure Security Center here. And we use this to kind of train machine learning models. We give analysts a feed of real attack data so they understand emerging attacks and they can write detections for it. We test our detections against this data. And we've improved our detections by about 75%. And it gives analysts more time to spend on the real emerging attacks. And when you opt into ASC, you get these alerts here. And a lot of these are based off this data. If you're interested in more deception stuff, this is Cliff Stoll, and this is his book. And I really recommend that you read it. Cliff was doing this kind of deception stuff, years and years and years before it was popular. So it's a really interesting book to read. So I'll leave you with this, to say that Microsoft is using deception technology to protect customers. Crucially, we want to understand the attack and the attacker, because if we can write detections for the attacker, well, that gives us loads of attacks. If you want to start using this, you should be using AZ Setpack or Azure Security Center. And if you've got big data and you don't want to care too much about how to process it and you just want to run queries, you should be pushing it into Log Analytics because it's great. Okay, that's the end. And I can get all those things.